All right, let's dive into something that sounds like it's straight out of science fiction, but is actually one of the most fundamental ideas in math. We're talking about the strange reality of imaginary numbers. So here's the big question, the one that really broke mathematicians' brains for centuries. How can a real problem have an imaginary solution? I mean, think about that. How can you solve a concrete problem using numbers that people thought were, well, impossible? This wasn't just some fun little puzzle, it was a full-blown crisis that made people question what a number even is. Okay, to get to the bottom of this, we gotta jump back in time. We're heading to 16th century Italy. And let me tell you, it was a time of fierce mathematical battles. The top minds were all trying to crack a huge problem, finding a general formula to solve cubic equations. And right in the middle of all that competition, they stumbled onto something that would completely change the game. So, have a look at this. It's an equation. X cubed minus 15x minus 4 equals 0. Looks pretty harmless, right? It's just a cubic equation, and you can actually find a solution just by trying out some numbers. But the big formula they were all after, the one that could solve any cubic equation, well, that formula had a really weird secret hidden inside. And here's where it gets crazy. The answer is just 4. A simple whole number. You can check it yourself, right? 4 cubed is 64. 15 times 4 is 60. 64 minus 60 minus 4. Yep, that's 0. It works. But, and this is the kicker, to get that perfectly normal answer using their new fancy formula, a guy named Raphael Bombelli had to calculate something insane, the square root of negative 121. And back then, that was just nonsense. Everyone knew you couldn't take the square root of a negative number. Or could you? This was an absolute bombshell. See, before this, whenever the square root of a negative number showed up, mathematicians would just toss it out and say, nope, that's meaningless. But now, they couldn't ignore it. It was a mandatory step to get to a perfectly real, solid answer. It was like, to find a real treasure, you had to take a detour through this strange, impossible, imaginary land. And suddenly, these weird numbers weren't so easy to dismiss. So they were useful. But just because they worked didn't mean everyone suddenly accepted them. Oh no. It took literally centuries for mathematicians to wrap their heads around what they discovered and to finally give this bizarre new thing an official name. And get this quote is from almost 300 years after Bombelli's breakthrough. It perfectly shows how torn everyone was. They were saying, look, these things are void of meaning, absurd. But at the same time, they admit they're of great utility. So the math worked, but it felt like cheating, like it was breaking all the rules of logic. And that feeling, that deep skepticism, it stuck around for a very, very long time. Eventually, though, they had to give this problem child a name and a definition. So they called it the imaginary unit I. And its whole job is super simple. I is the number that when you square it, you get -1. That's it. And fun fact, the name imaginary, it was actually meant as an insult. The famous philosopher and mathematician René Descartes coined it to show just how fake he thought these numbers were. I bet he had no idea that his imaginary number was about to find a very real home. So what was the big turning point? How did these imaginary numbers finally convince everyone they were real? Well, the breakthrough didn't come from more equations. It came from pictures, from geometry. It was a huge flash of insight that suddenly gave these numbers a physical, visual meaning you could actually see. Okay, so you know the normal number line, right? It just goes left and right into the positives and negatives, one single line. The massive leap forward was this idea. What if imaginary numbers aren't on that line at all? What if they exist in a whole new dimension, shooting straight up and down, perpendicular to the real one? And when you put those two lines together, the real axis and the imaginary axis, bam! You don't have a line anymore. You have a two-dimensional plane, a map. And they called it the complex plane. And that was the big aha moment. All of a sudden, a so-called complex number like a+bi wasn't some weird abstract thought experiment. It was a point on a map. It had coordinates. You go A units on the real axis and B units on the imaginary axis. It had a location, a physical spot you could point to. It went from being a ghost to being a place on a map. And the thing that really sealed the deal was that the geometry lined up perfectly with the algebra. I mean, look, when you add two complex numbers with algebra, you just add the real parts together and the imaginary parts together.
Simple enough. But when you represent them as arrows or vectors on that complex plane, adding them geometrically works exactly the same way. You just put them head to tail. The rules were the same. This wasn't some fluke. It was a real, solid, logical system.
So once they had this solid foundation, both visually and algebraically, complex numbers started to, well, they started to show off. They began unlocking some of the most profound and beautiful secrets hidden deep inside the world of mathematics.
This all leads to something with a very grand name, the fundamental theorem of algebra. And what it says is just incredible. It guarantees that every polynomial equation, no matter how complicated, has an answer. Even an equation like x squared plus 1 equals 0, which has no solution on the real number line, always has a solution on the complex plane. The system was finally complete. No more dead ends. Every question had an answer.
And out of this beautiful, complete system comes what is, hands down, the most beautiful equation in all of math. Seriously, mathematicians call it a poem. It's Euler's identity. And just look at it. It ties together 5 of the most important numbers in the universe. E, pi, our new friend I, 1 and 0, all of them connected in one simple, elegant, and, frankly, kind of magical statement.
Okay, so it's beautiful, it's elegant, but you might be thinking, so what? Is this just a neat party trick for mathematicians? Well, here's the final twist. It turns out this imaginary world isn't just in our heads. It's the hidden source code for our actual physical reality.
I'm not kidding. This isn't just theory. It is the bedrock of our modern world. Your Wi-Fi signal, your 4G connection, they are processed using complex numbers. The control systems that keep airplanes flying straight, the ones that guide robots with incredible precision, all complex numbers. And it goes deeper. The fundamental laws of electricity and magnetism, how water flows, even the mind-bending rules of quantum mechanics, they are all written in the language of I. This imaginary number is literally what makes our real world tick.
And if that's not enough, on top of all that utility, they create some of the most stunning art you've ever seen. This right here is the Mandelbrot set. Every single swirl, every infinitely detailed pattern you see is generated by one incredibly simple equation, just repeated over and over again in the complex plane. It's an entire universe of infinite complexity born from one tiny rule. And this world, this beautiful, impossible fractal, it just wouldn't exist without I.
So think about that journey. We started with what everyone thought was a mathematical mistake, something absurd needed to solve an old algebra problem. And we ended with a fundamental tool that not only describes our physical reality, but also creates infinite beauty. It really makes you wonder, doesn't it? What other impossible ideas are floating around out there today, just waiting for someone to look at them from a new angle and unlock a whole new reality?